Hi, this is section 3.2, talking about polynomial functions. Today we've got 6 topics. A polynomial function is a function that is the sum of powers of x. So it's written, like here, showing you all those little possible powers of x. It looks a little overwhelming written that way, I think, but we're just talking about different powers of x. So like f of x equals 4x to the 5th power plus 2x minus 1. Or g of x equals negative 7x to the 4th minus 3. Just different powers of x that are being added together. We talk about these it can have lots of terms. It can have 2 terms. Quadratics are one type of polynomial. So like 2x squared minus 3x plus 4, that's a polynomial. It just happens to be a degree 2 polynomial. We talk about polynomials in standard form most of the time. The degree of the polynomial is its highest power when it's in standard form. And the domain of these polynomial functions is all real numbers. There aren't any x values that are going to give us errors or issues because we can always square a number, no matter what number it is. We can always raise it to a power. The graph of a polynomial, when you look at it, is smooth and continuous. They're curvy things. We oftentimes will factor polynomials in order to reveal information about the polynomial. Factored form of polynomials gives you information about the zeros or roots or x-intercepts of the function. So if a polynomial has a factor of x plus p, we know it has a 0 at negative p on the x-axis. If it has a factor of x minus q, we know that it has a 0 at q. If it has a factor of x minus r, we know that it has a 0 or a root at r. So like, for example, on this graph, if I knew that it went through the x-axis at negative 5, negative 1, 1, and 3, for example, I could write, or I could know that it has a factor of x plus 5, x plus 1, x minus 1, and x minus 3. So the factored form gives us a lot of information about the roots of the function, or the zeros. So our first topic is that we want to state what the zeros of the polynomial function are if that polynomial is given to us in a factored form. So we're looking for the real zeros of these functions. So look at the factored form of the function, and for each of the x's, you will have an associated 0. So if we have a factor of x up at the front there, that goes with the 0 of 0. If you have a factor of x minus 8, we know that it has a 0 at, positive 8. Getting happy with my negatives here. And then this one that has a power of 2 here, that tells us that we have a couple of possibilities. And if you look over at our next example, I have the other 2 sort of possibilities that might happen here. X squared minus 9 is just not fully factored yet. That is the factor x plus 3 multiplied by the factor x minus 3. So if you have a power of 2, it may be that you have some additional factoring to do. So our 2 additional roots are negative 3 and positive 3. So that's a list of the zeros. When you're typing in your answers, you just need to separate those answers with a comma. The next polynomial, g of x, also in a factored form. We're looking for the zeros of the function. Now you'll notice there's not an x with this negative 3 like there was over here. If there's not an x up at the front, it does not have a 0 of 0. So that's not contributing a 0. That negative 3 is a type of stretch or reflection stretch. I also have a power of 2 here. A minute ago when we had that power of 2, we were able to factor, and you might remember like how to factor that. We can factor it in the complex numbers as x plus 2i and x minus 2i. But in this topic, we're looking for real zeros. So this is not contributing any real zeros for the function. So we don't need to list any associated with x squared plus 4. So if you have an x squared with a constant like x squared minus 9, x squared plus 4. If it's negative, you're going to want to factor it. If it's positive, that would factor into complex numbers, and you don't need to. So this factor is actually giving us our first 0 for our list. If we have a factor of x minus 1, we have a 0 of positive 1. All right, we've got one more instance where we have squaring in our list, and this time it's an x plus 6 that is itself squared. So if we were writing out this polynomial g of x, it would look like this. X plus 6 squared means x plus 6 is a factor of that polynomial twice. So we don't actually need to list that negative 6 twice. It's just a repeated factor, and you don't need to repeat it on your list. In fact, that type of factor, we would say that 0 or that root has a multiplicity. So if we have a function f of x that has an x plus c squared, then we would say the 0 negative c has a multiplicity of 2. If it had an x minus b factor that had a third power, we would say that the 0b has a multiplicity of 3. So if you have repeated factors in your polynomial, they have roots with multiplicity, and they are roots of the function. You can see them on the x-axis when you look at the graph of the function, but the behavior at those roots with multiplicity is a little bit different. If you have an even multiplicity like 2 or 4, like maybe this is an x plus 4 squared, what you'll see is that the function just goes right up to the x-axis, touches at that 0, and then turns around. Kind of like if you zoomed in like a little mini parabola. So that's if it has an even power, an even multiplicity on that root. If you have an odd multiplicity like 3 or 5 or 7, you'll see behavior where it goes up, approaches that root, touches it, and then continues on. But what it does is it kind of flattens out a little bit. It's called an inflection. So a power 1 won't do that if it's just like a regular factor like x minus, I'll call it d. If it has just that regular factor, it would just go straight through. It wouldn't flatten out at all. But if it has a higher power that's odd, like 3 or 5 or 7, it does flatten out. So this next topic just asks us to list the zeros, and we're just listing them grouped by their multiplicity. So looking for the zeros of multiplicity 1, you're looking for the factors that just have power 1. So in other words, you don't even see a power written there because it's just power 1. So we would just list positive 6 and negative 4 for the 0 of multiplicity 1. For 0 of multiplicity 2, we're looking for the factors that have a power of 2. So we would list the 0, negative 11. And for zeros of multiplicity 3, we would look for factors that have a power of 3. So we would list negative 8. If you have one that doesn't have any, so for example, if this said zeros of multiplicity 4, we would just say that there is none. So you might have none on them. Okay. So the next few topics have to do with sort of the shapes of the graph and drawing graphs and analyzing graphs. So when we look at a polynomial function that's in standard form, that leading term gives us a lot of information about what is happening on the far sides of the graph. It doesn't tell us a lot about what's happening in between there. You know, it may just connect, it may wiggle, it may do a lot of things, but the leading coefficient does tell us a lot about the ends of the graph. So if we have a polynomial that has a degree 4 power, like maybe we have 3x to the 4th plus 2x minus 1, again, focusing on that leading term tells us a lot about the polynomial. So for this one, the degree of that polynomial 4, that's an even number. And when we're thinking about end behavior, we aren't really thinking about we don't care that it's the number 4. We're thinking about if it's even or odd. So that's an even number. And the leading coefficient of this is 3. And what we want to think about and focus on when we're thinking about our leading coefficients is whether they are positive or negative. So this is a positive leading coefficient, and it's an even degree polynomial. So what that tells me is that if I look at a graph of this polynomial, I don't really know what's going to be happening in the middle, but I do know that on each side, it is going to be positive. It's going to be going upward. And that's true for every even degree positive coefficient polynomial. It's going to have both ends up. It might have some squiggles in the middle. It might just be a parabola. We don't know what's happening between those two ends, but we know that both ends is going to be up way high. And in part, that's just because if we take a negative number and we substitute it into this polynomial, we're going to be raising it to the 4th power. It's going to be a positive number. And the other terms, like the 2x and the -1, they're so much smaller in magnitude than that leading term that the leading term is sort of the boss. It's sort of controlling the behavior. If you had a negative coefficient, what that does is reflect it. So instead of both ends going upward, a negative coefficient reflects it so that they're now going downward. All right, with an odd degree polynomial, like maybe f of x equals 4x to the 3rd power minus 7, if you looked at the ends of that, you would see that this one is up high, because if we raise positive numbers to an odd power, they're still positive. But on the negative side, if we substituted a negative power into this, a negative power raised to the 3rd power would be negative. So we have the two ends are doing different things. On the right, it's going downward, and on the left, it's going upward. So that's the behavior we see with odd degree polynomials with positive coefficients. And again, if you have a negative coefficient, it just reflects it so that right side is going downward and the left side is going upward. And you need to understand this chart, and you need to understand, which powers and which coefficients are going to give you which behavior. And it's not on your reference sheet. So you just kind of need to sort of internalize that. So this topic is asking us to choose the correct end behavior for each of these polynomials. And I like to think about them and draw myself a little sketch. So this is an even degree, and it is positive coefficient. Positive even. So even means that both ends are going to be the same, and positive means that they are both going to be going up. So this categorizes it with left hand first. Oops. So we've got the left hand listed first and the right hand listed second on our choices. So thinking about the left hand side, it's rising to the left. And it is rising to the right as well. So it looks like we need to choose this choice right here. Rising to the left, rising to the right. And just make sure you're reading those carefully. Our next polynomial has an odd degree. And when we're looking at a polynomial in standard form, we are just focusing on that leading term. And this coefficient is negative. So that's a negative odd polynomial. So odd means the two ends are doing opposite things. One's up, one's down. Negative reflected it. So it's going to look like this. So it is rising on the left, but on the right, it is falling. So that's going to be this second choice. The last one is in factored form. In factored form, it's a little bit harder to figure out because it is end behavior is the easiest to see from standard form. So what you want to think about is how many factors this has In fact, this one has a multiplicity. So remember that multiplicity just means that it's a repeated factor. So this has 1, 2, 3 factors. Just if you don't write it out, make sure you count that multiplicity. So this is a degree 3 polynomial. And if I think about, multiplying that out, it would have a coefficient of 3 right here. So that is positive. So this is a degree 3 positive polynomial. So it would look like this. Degree 3 is an odd degree, so that means the two ends are doing opposite behaviors, and it has a positive coefficient, so it is increasing to the right. So it is falling to the left and rising to the right. So it's that first choice. Fall to the left, rise to the right. All right, our next topic, it's going to give us a graph of a polynomial, and it's going to ask us about its increasing intervals or perhaps decreasing. It's going to ask you about the relative extrema. It's going to ask you the sign of the coefficient, and it will ask you what possible degrees it might have. So here's our graph to help us. The first thing it asks us is, where is the function increasing? And just make sure you read yours because it might ask about decreasing. So for increasing and decreasing, make sure you read the function from left to right, like you're drawing it. So at first, this function is decreasing, then it's increasing, then decreasing, increasing, decreasing, increasing. So like a roller coaster, read it from left to right. So our intervals of increase, I'm highlighting yellow, it would be from -8 to -4. And then that next one starts at 0 and goes to 5. And then from 9 to infinity. So you'll just look for and match up those ones. It has to match perfectly. It can't include more or less than exactly where it's increasing, or if yours says decreasing, decreasing. All right, the next topic asks for local minima. So make sure you find only the minima, not the maxima, or vice versa if it asks you for the maxes. So our minima are low points on the graph. They don't have to be the lowest. They just have to be a low point in their region. So we have 3 local minima, and it asks us for their x values. And we will list them separated with a comma. So our first minima occurs at -8. Our next minima occurs at 0. And our final minima occurs at 9. And notice that those minima happen when the function is changing from decreasing to increasing. Okay, what is the sign of the leading coefficient of this polynomial? Well, for the sign of the leading coefficient, we're going to think about the end behavior. For this polynomial, both ends are up high, so this would be a positive leading coefficient. It's not asking you for the number that the coefficient is, it's just asking you whether it's positive or negative. Okay, and then the last one asks for the possible degree of the function. For possible degree of the function, you want to think about the intercepts or the wiggles, or how many changes are happening. Now, both ends are the same. So we know that this is an even polynomial, an even degree polynomial. So we know that it can't be degree 5, degree 7, or degree 9. It's even. It's got to have an even degree. So if we think about our wiggles and how many times this thing changes, it changes 1, 2, 3, 4. I'm not good at counting these. 1, 2, 3, 4, 5. Changed 5 times. So it could be degree 6 or 8, anything higher than the number of changes. If it has a lot of, if you can see all the zeros, 1, 2, 3, 4, 5, 6 zeros are present. So that's another way to count for degree, the degree. Just don't forget to count multiplicities. So you can either think about changes and add 1 to get the lowest degree, or you can think about zeros. Be careful for a function like this. If it goes like wiggle, 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 you would have to count changes on that one because you can only see 1, 0. But if you counted the changes, this changes 1, 2, 3, 4, 5 times. Oh my gosh, 1, 2, 3, 4 times. It would have to be degree 5 or higher. Okay, our topic here is asking us to match the graph with the polynomial. So it'll give you two polynomials. One of them is not in a factored form, and the other one is in a factored form. And your job is to match it over. So for a factored form polynomial, the first thing I would think about is the zeros. This has a 0 of -1 with a multiplicity of 2 and a just regular 0 of 3. So that means we should see a turnaround at -1 and it'll go through at 3. So it couldn't be this one. It doesn't have a turnaround at -1. Ah, this one looks good. So it could be graph B, possibly B or that one does not have a 0 at -1. Ah, this is another potential candidate. Turns around at -1, goes through at 3. B or D. So those are the two possibilities. If you look at the rest of them, they do not have the right intercepts. So we're looking at -1 and 3. So these ones don't work for what we're looking for. Okay, so we've eliminated it down to just B or D. So then we could think about our end behavior if we wanted to. This is a degree 3 polynomial, and it looks like it would have a positive leading coefficient. Because we've just, we don't have a negative in front and all of our x's are positive, so that's going to be a positive coefficient. So the one that has the correct end behavior is graph B. Graph D would have a negative coefficient, so it's not graph D. All right, so then our next polynomial is not factored. So I might first look at the end behavior because end behavior is easiest to see from standard form. This is degree 4, so that's even, and this is definitely a positive coefficient. So that means both ends would be up high. So it looks like we have the possibility of graph C or graph E. Graph F, both ends are down. So it cannot be F, possibly E or C. So then to figure out which of those two it is, what you would want to do is factor it. These ones, when I scrolled through them, none of them looked particularly challenging to factor. The first thing you'll want to do is look for a common factor. So these two terms have a common factor of x to the third. Factor out that common factor and you'll either be done or you may have a quadratic to factor. So look for a GCF, a common factor there. So it looks like we have a 0 at 3. Oh my goodness, yes, at 3, and a 0 at 0 with a multiplicity of 3. So it should have sort of a flattening out of some sort at 0, and it should go straight through at 3, probably down. So if we look at our graph, it looks like E has a multiplicity of 2 and a multiplicity of 2, so it's not going to be that one. Here we see our little flattening out and our straight through behavior that we were looking for. So this one is graph C. And I think with practice, you get a lot faster at matching these up. Okay. The last topic in 3.2, I think, is the trickiest one, and that is that we have a polynomial given to us and we have to graph it. And the way Alex has you graph these, I think, is a little bit challenging. It will also have some questions that you'll answer on your path towards graphing. So the first thing it's going to ask you is what end behavior does the function have? So this polynomial that I have, oh, I think in your notes I gave you a different one. I think, let's see, I'm just going to change it. This might not be exactly the one in your notes because I don't have that with me right now, but this is closer to what you have in your notes than the one I have in here. Okay, so let's go with this polynomial. So you'll look at it, you'll try to decide what degree it is and if it's a positive or negative coefficient. So this one, the degree, well, I have 1, 2, 3, 4, 5 factors. A total of 5 factors means it's a degree 5 polynomial, so that's odd. And the leading coefficient, look for things like a negative that's leading. Make sure that your x's are positive. In this case, it is going to be a negative leading coefficient. So odd degree negative coefficient means that our end behavior is going to look something like this. So it looks like it's going to be rising on the left and falling on the right. So this is our choice right here. Rising on the left and falling to the right. Super challenging if you're like me and you don't know your right from left very well. All right, the next one's going to ask you to list the zeros of the function, and you have to say whether it's going to cross or touch, but not cross the x-axis. So when it crosses, that's going to be an odd multiplicity for that factor. And if it touches but not crosses, that's going to be an even multiplicity. So for our odd multiplicity, our crossing the graph is going to happen at -3. Our other two factors have an even multiplicity, so we would list our 1 and our -1. Okay, it's going to ask you to find the y-intercept of the function. Just sub in 0 to find the y-intercept with polynomials and with all other functions. Just sub in 0. So this is -0 plus 3 times 0 minus 1 squared times 0 plus 1 squared. Don't neglect a negative at the front if it's present there. So this would be that f of 0 is -3. And you could type that in your calculator or do it in your head. All right, and then we need to graph it. So it's a little bit challenging to graph. My advice to you would be, before you even start plotting it in Alex, is to just make a rough sketch. So start with your end behavior. We know this side is down and this side is up. We know that it's going to go through the y-axis, that's our y-intercept, at -3. And we know that our zeros are -3, -1, and +1. So I'm going to, these red ones are where it just touches and turns around. So I know it goes straight through here. The next one is -1, but it's going to turn around. It's going to go through that y-intercept. It's going to turn around again, and then it's going to go down. And it can be kind of hard to figure that out at first. Just make sure you maybe pay attention to where it's going to turn around. So when you plot this on Alex, you are going to mark the intercepts. But when you mark those x-intercepts, you have to kind of click, and it will give you a choice, a set of choices that look like this. It's going to be like straight through, turn around above, or turn around below. So when you plot it, you're going to plot this one. You have to tell it that it's doing this. So you would click on that button. And then when you plot this one, you'll have to select that it's doing this behavior right there. So it'll put like a little thing with it. And then you'll have to select that again for this one. So drawing this first will help you put it into Alex a little better. And then when Alex draws it, it's going to be a lot, maybe different looking from the one you did. on your sketch because it's going to be drawing it sort of exactly. But it will make you plot those intercepts, including the y-intercept, and then you can just click on the graph icon and it will draw the polynomial. I think this is a pretty challenging topic. Just do that rough sketch first, I think, before you try to transfer it into ALEKS. All right, so I think that's it for, yep, that's it for 3.2. I'll make a separate video for 3.3. Let me know if you have questions. Thanks.